Hello friends, welcome back to Quantum Quandary. Today we're going to discuss the full one-dimensional Doppler effect. Last time I only considered when we have a stationary source and an observer in motion, and I kind of disentangled the two cases when the velocity is away or towards the source in the radial direction, or since we're in one dimension, just in the one direction. Now we're going to consider all the cases if the source is moving, if the observer is moving. So we're going to assign a velocity v to the observer whose positive value is in this direction. But if we have negative v, we just change the direction. What we do limit it is to be under c, where c is the velocity of the wave that's being propagated by the source. Similarly, we ascribe a speed. I should rather say speed than velocity, but I prefer to say velocity. A speed u to the source, which is also less than c. Okay, when it's greater than c, we don't have the Doppler effect. We just have something moving faster than the light it's emitting. So, yeah. And this is all we're going to consider. Now we're going to look at first what happens with the source. Since with the observer, the moving observer, we know from the last video what happens. We are going to show that as well though. So when we have the source, I like to draw it this way. We have a source here at time equals 0, and it's just about to emit a wavefront, right? And then at, say, time equals t, which is the period of the wave, right? At time equals t, we have the wave, well, let's just draw it like this since it's one-dimensional. So these are the wavefronts. And it's beginning to fire a new wave, right? This would be if it were stationary. So if it were stationary, this would be ct, right? The speed of the wave times how much time it has traveled, that's the distance traveled by the wavefront. But, and this distance is definitely ct. But the wave, the source is not there anymore. The source is now somewhere here because it traveled its own speed. It traveled its own distance, by using its speed u. So obviously it traveled ut. The time it took is t and u is the speed. So it traveled ut units of distance. So what's left? Well, this thing is going to be the apparent wave period in this direction. So we're going to call that ct prime. Let's use prime. And obviously over here, we would also have a ct prime or some other ct prime. So we could call it ct second. That would be the apparent change in the other direction. But in this case, u would be negative, right? So we're just gonna, it's a symmetric problem, right? Or rather anti-symmetric because u goes to minus u. So from this, we can say that ct prime is ct minus ut. And now from here, you see that if u is greater than 0, which is our case, then t prime is less than t, right? We can factor out, we can say that this is c minus u times t. So t prime is larger than t only if u is negative, which would be this part. This would be ct prime if we were looking in the other direction. And indeed, every source kind of makes two Doppler effects in one dimension. One that is observed on the side where it's coming towards, and one that is observed on the side that it's leaving, right? And the two are anti-symmetric with respect to the speed, the sign of the speed. So this is what we get. Now notice this CT prime, we can use this as the new period of the wave. So looking from the right, if I look from here, I'm the observer, and I'm looking from here, what I see is not a wave of CT, of period T, or lambda CT, but I see a, so many C's, I see a wave of CT prime, of lambda prime, okay? So now let's see what the observer looks. This was only the case for S. Now we can just shift the time scale. I'm not gonna, I'm just going to shift it back to t equals 0, okay? Because this holds regardless of t. It's I mean, regardless of little t, regardless of time, this holds. So I can shift the time scale back or forth, and this is the observer, and I again consider the observer being reached by one wavefront. So this is wavefront 2, this is wavefront 1, and we're being reached by this one wavefront. But now this distance here is lambda prime, which is CT prime, okay? That's what we're observing here, and CT prime from here. And then this is time equals 0, okay? This is the first time slice. And then in the time slice, t equals t second, yt second. So here we had, the solutions are not symmetric. Here we had t, the period, because the wave, the source is very connected to the wave, so to say. But here we need this time to catch up, right? I mean, you can check the previous video. Because, okay, so from here, the first wave is gone, okay? We don't care. The observer is somewhere here, it moved away. And, well, let's look at t equals t prime, actually. Let's look at t equals t prime. So these two guys are still divided by CT prime, right? It's gotta be true. Let me just make the colors consistent. That's always true. They're not gonna dilate in between. So, but instead of wave 2 reaching the observer has moved away by VT prime, okay? The observer moved away by VT prime. That's just it. So what we actually need to wait for is we need to wait for this wavefront 2 to reach the observer, and this happens at some seemingly arbitrary time t second. It's not arbitrary, but we don't know it yet. This happens at some time t equals t second. All right, so the observer is finally caught up by the second wave. This is still CT prime. This is still CT prime. And now if we compare these two, we have that the observer has traveled VT second, right? I guess we don't really care about this part anymore. The observer, let me just stop drawing this part. And instead draw a flashback of what we had before, okay? So what we had before was this and this. Yeah, there we go. So what we had was this. This is a flashback from t equals t0, or from t equals 0. So this is CT prime. And then this was where the observer was. Maybe I should draw that in green as well. This is where the observer was. And the observer moved away by VT second. So that means that the second wavefront had to catch up by CT second. So what we need is that CT second is equal to VT, well, let's use CT prime plus VT second. The way I'm writing it means that if V is negative, then T second is less than T prime, right? Or, well, maybe let's group that together so that that's obvious. There we go, like that. And we can express T second as C over C minus V T prime. And now we need to plug in this. Oh, CT prime. Okay, so we can have CT prime. CT prime. So Ct prime is c minus u times t. That means that t second is c minus u. U is the speed of the the source, and then c minus v. V is the speed of the receiver, the observer. And here we have t, the regular period, and of course, since t is 1 over frequency, we also have that the observed frequency is c minus v over c minus u times the original frequency. So you move away from a wave source, frequency is gonna fall down. You know, you have the wave source moving closer to you. What do we have? Then u goes up, this goes down, so the whole thing goes up, frequency increases. Makes sense, right? Wave is coming closer to you, you get more ticks of it. This is the final formula for a one-dimensional Doppler effect. Yeah, hope you guys enjoyed it. Bye-bye.